Okay. Okay, yeah. Okay, so for okay, thank you. For today, both Swarab and I are together in sunny Manchester, and really like to welcome you to this third day of our thermal spray week. And I think I've said everything that needed to be said at the previous events. So we really look forward to two more really interesting talks from Shrikant and from Armel. Thank you.
Great, thanks, Alan. So today is led by Europe. We had our first day, which was led by the West. We had then the Eastern dominance yesterday, and now today we have the dominance of Professor Shrikant Joshi from Sweden and from Professor Armel Bordel from France. And tomorrow we will have a dedicated ECR session, which will have a combinatorial ECRs coming from all over the globe. So on that note, I'd like to begin the introduction of Professor Joshi, who, as I said in one of the earlier talks on the day when Professor Sanjay Sampath was introducing him, that beside him is one of the other finest export from India in the thermal spray area. And currently he's a professor in the Department of Engineering Science at University West in Sweden, with nearly 30 years of experiences in areas spanning surface engineering, laser materials processing, and now spanning that through additive manufacturing as well. By education, he's a chemical engineer and has obtained his MS and PhD degrees from Rensselaer Polytechnic Institute and University Dow in the US. And prior to move to Sweden, he had long stints as a scientist at a couple of premier federally funded materials research laboratories in India, including ARCI. His past work has attempted to bridge basic research, technology development, and its transfer for industrial implementation. And his current areas of research are solution and solution powder, hybrid thermal spraying, and additive manufacturing. His work has led to many industrial applications, over a dozen patent submissions, and more than 200 publications in peer-reviewed journals. And he's also very vocal on social medias, especially on LinkedIn and Twitter, to promote his ECRs, especially the PhD students and postdocs. So on that note, I'd like to now invite Professor Joshi for giving us your talk, and we look forward to listen to you.
Thank you, Saurav and Alan, for this wonderful opportunity to share some of the excitement from our lab at this thermal spray week. It's really been fascinating listening to talks over the first 2 days. That, however, puts additional pressure to match what you guys heard over the first couple of days. It's a slight relief that I go before Armel, because she's a hard act to follow, but I'll do my best. What I'm going to be talking about today is mainly our experiences with employing liquid feedstock to realize different functional coatings employing thermal spray. But before I dive into the subject, a big hello from Trollhättan, where University West is located, on behalf of my colleagues here. If you've not heard of University West before, don't feel too bad. Even I had not heard of it till I actually moved here, pretty much. It's situated close to Gothenburg, which is Sweden's second largest city, and it's been kind of a fairly well-hidden jewel as far as the engineering landscape in Sweden is concerned. It used to be the town of Trollhättan used to be the home of Volvo Aero, which is now GKN Aero, and also of Saab before it went belly up. Talking about our university, it's fairly young, one of the youngest universities in Sweden, founded in 1990. But what might surprise most of you is the fact that the university got its PhD rights only in 2012, so just a decade ago. So, however, in that very short time, I think the university has established quite a niche for itself, particularly in the field of production technology. So The university's research in production technology spans many different areas. Thermal spray, incidentally, was the first research area, thanks to proximity to Volvo Aero. But now we do a fair bit of work in the areas of machining, metal forming, robotics and automation, and of course, welding that has almost naturally kind of blossomed into additive manufacturing. Our thermal spray group is a modest sized one. We have 3 or 4 professors, a couple of PhD students. We've also had a culture of periodically inviting the best known names in thermal spray as guest researchers. So right now we have Robert, Professor Wasson as the guest researcher. Prior to this, we had Sanjay, and even before that, we had Ping Xiao from Manchester as a guest professor here. We have a couple of neat toys. What you see operating right now on your screen is an HVAF. We also have an axial feed capable plasma spray torch. And these 2 toys really are the secret behind how productive our thermal spray group has been. Let me also get some important acknowledgements out of the way, because I'm just a mouthpiece for some excellent work that is done by my colleagues. You see my colleagues here, several postdocs that have kind of passed through this group. Many funding agencies, I specifically mentioned this Swedish funding agencies, but also Department of Science and Technology in India, because that is honestly where my experience with liquid feedstock started. And several collaborators. It took a while to convince some of them that liquid feedstock is interesting, but yeah, now we have a fairly large network of people who are as excited as I am about using suspensions and solution precursors. And of course, a big thanks always to our industrial partners. The list seems to keep growing. Not so much in use of liquid feedstock alone, but also what we do with HVAF and using the axial feed capabilities of the plasma torch. Alan says this is a thermal spray week. I'm going to take the liberty to digress for a minute or two and talk about something very exciting that we did in our lab less than 2 weeks ago. And that was to put on a luminescent coating on this target wheel, which is the heart of the European spallation source that is being built here in Lund, or integrated, I should say, here in Lund, south of Sweden. But it's an activity that involves collaboration amongst 13 European countries. So it was awfully exciting for us to be able to coat this target wheel for the European spallation source. It's 2 meters in diameter, weighs more than 6 tons, and you don't want to know how much it costs. I mean, that made us a little bit nervous, but yeah, it was great fun coating these different segments on the target wheel. So maybe more about that at another time. Right. Let me then get to the theme of my talk. Please don't be scared by the slide that you see. I'm not going to get into the basics, but just to put this in perspective, and I mean, what I'm going to talk about liquid feedstock, to put that in perspective, and just in case there are new people in the audience, especially students. So very quickly, how is thermal spraying conventionally practiced? You introduce a material from which you want to form a coating, sometimes in rod or wire form, but typically in the form of a powder. And the idea is to melt this material, accelerate it to a high enough velocity so that it forms splats, which are like pancakes on the part which is to be coated. And you overlap these splats to cover large areas, and you stack up these plats to build thickness, right? So typically that's how thermal spraying is practiced. And what is usually the intent? The intent is to ensure that the powder particles that you introduce are fully molten to obtain dense coatings, and they also impact the substrate at the maximum possible velocity, because uh, uh, these are, you must remember, mechanically anchored coatings, so the adhesion strength is kind of well correlated to the impact velocity. So these are the conditions that I highlight usually trying to meet. And because of this reason of high particle velocity, typically the residence time is of the order of milliseconds. So all the action, melting, acceleration, impact has to happen in the order of milliseconds. Now, if you look at the spray grade powders that are out there, uh, typically there's an upper size limit, which is dictated then by what can you melt during this short residence time. So for relatively lower melting metallic powders, it could be slightly high. The upper limit could be 90 or 100 microns. For ceramics, it's lower. And then, yeah, of course, depending upon what process you use, it could change a little bit. But this is the reason for having an upper limit on your powder feedstock, which is easy to appreciate. But then there is also a lower limit, which is often dictated by the flowability of the powders. And then typically, if your powders are 5 microns or lower in size, it's difficult to reliably feed them, and therefore also to reliably coat them. And that really takes us directly to the motivation for employing liquid feedstock. So this is the most convenient avenue then to create finely structured coatings without encountering the feeding problems that are normally associated with use of few micron, submicron, or nano-sized powders, and thereby realize some very unique microstructures. So there are two ways to do it. The simpler of the two options is to kind of put these fine powders into a suspension using an appropriate liquid medium. The more difficult approach, of course, is to not use a powder at all, but use a suitable salt solution, which will hopefully form the material of interest in situ, right? And examples of these kind of salt solutions are typically acetates or nitrates. Sometimes chlorides are used as well. And these do allow for very rapid exploration of new precursor compositions or their combinations. Most of all, they circumvent the need for using powder feedstock completely, right? This use of liquid feedstock, is it radically different? Depends on perspective then. So there is a very simple cartoon of what a conventional plasma spray process looks like. You have this plasma spray torch, there's a powder that you introduce radially, and all the heat up and acceleration happens as we spoke about a moment earlier, right? When it comes to liquid feedstock, the only thing that really changes is that the powder delivery is replaced by a liquid feedstock delivery, right? The nice thing from my perspective is the fact that it uses conventional thermal spray hardware, right? And therefore, adoption is relatively easy for existing thermal spray users, right? All that you need is a reliable liquid feedstock delivery system. And there's increasing number of those available now. This is an example of the type of liquid feedstock feeder that we have. But yeah, it's as good as any powder feeders now with closed loop control, mass flow regulation. You could even combine multiple liquid feedstock feeders. Some of these have twin tank versions. So yeah, if you buy the right feeder, and you have an existing thermal spray hardware, you're ready to go, right? I wish life was that simple, but we'll get into that as we move along. One thing to remember, and I think that's easy to appreciate, is the fact that the use of a liquid feedstock has higher energy requirements associated with it, right? What you see on this cartoon is uh, uh, from a publication very early on when people started looking at solution precursors, right? A lot of things need to happen for the precursor to get through gelation, then pyrolysis, then hopefully the powder of interest is formed in situ. And then this powder from this point on kind of behaves like one would expect: melting, acceleration, formation of splats, right? But all of these steps require significant thermal energy. So if you were to go hunting for thermal spray literature employing liquid feedstock, you would find most of the early work utilizing plasma spray torches, right? Because of this need for high thermal energy. Suspension plasma spray, solution precursor plasma spray are good keywords if you want to start looking for earliest literature on this subject. Of course, as we understood the subject more and more, we got a hang of how the liquid feedstock behaves in a thermal spray torch. People have started kind of dialing down the thermal energy content and still get good coatings using HVOF, perhaps using HVAF as well, as I will attempt to show towards the end of my talk. Right. So when we first started work using liquid feedstock, there were several initial concerns. Some of these I've listed here. One was that the processing window was quite narrow. The deposition rates were pretty dismal, actually, and one struggled to put on a reasonably thick coating. I remember our first year or two of solution precursor plasma spray. We need to spray coming in very close to the substrate, so there were substrate heat up issues. So yeah, I mean, if the jury was out then, most of them agreed that this was too far from being exciting on the shop floor, thermal spray shop floor, right? But that was then, because soon people realized that use of high power plasmas clearly begins to help when it comes to determining the deposition efficiencies, and you get pretty good numbers here, right? I mean, this is an old paper which provided very valuable insights into how plasma power can influence deposition efficiency when you use a solution precursor or a suspension. And for this reason, I think now is a great time for kind of diving into use of liquid feedstock. Why? Because there are some pretty good axial feed high power plasma spray systems that are available out there, and they can really be game changers, because I am of the opinion that liquid feedstock did not get a fair hearing when we were all compelled to use radial feeding, right? And the reason for that is when you use radial injection, the injection of the liquid feedstock is very sensitive to the injector diameter. It always is sensitive to the feed rate, particularly so when you inject it radially. And then, you do not utilize all the energy that is available in a plasma plume. And considering the fact that the liquid feedstock per se needs more energy, we were destined to have problems with radial injection. the ability to inject this feedstock axially kind of changes the game altogether, right? It allows very robust injection of feedstock. The deposition efficiencies have gradually crept up in a regime which is suddenly quite exciting, right? And uh, uh, this is achieved while enabling complete material treatment within the plasma plume as you desire, right? So just to recap before we move on, uh, of the two, uh, use of solution precursors and suspensions. Suspension is clearly relatively easier since powders are already present, suspended in a suitable medium. In contrast, solution precursors completely do away the need for powder feedstock, but then, yeah, you need to go through more steps, and therefore, it's far more challenging in terms of the process steps that are involved. Right? I did mention a little bit about uh, narrow processing window, etc. To go with that, one of our uh, early hurdles was really the fact that we could not use any of the in-flight diagnostic tools, which are now available, as you heard over the first couple of days, for conventional plasma spraying. They just do not work when you talk about generation of in-flight particles that are submicron, for example, right? So what we started doing during those early days is to attempt to carefully collect uh, or grab particles in situ, or what we thought was particles, and then also look at splats, and from then derive useful insights on how the process parameters may be impacting coating formation, right? Won't get into details at all due to lack of time, but uh, just to let you know that collecting these kind of particles in flight have a story to tell, right? I mean, many times if you're way off from the right processing window or the sweet spot, you essentially get just gel. That's what you collect, right? But if you do it right, you begin to indeed form particles of the kind that you would want to form, right, to get good coatings. So uh, this was a good diagnostic tool in a sense, right? Or alternative to conventional diagnostics. Similarly, the splat morphologies too are extremely educative. If you are way off kilter, you barely get splats. You get these gels or somewhat thermally decomposed salts. If you're way off, if you're right, you begin to get nice dish-shaped splats, right? I mean, and it's a little bit hard to see, but this is about just over a micron or micron and a half, right? So that's exciting. This is the kind of splats you would be looking for if you're seeking a refined coating microstructure, right? So as we went on, I think we learned more about what is the mechanism of coating formation. If you use solution precursors, right? I mean, it involved uh, flattening of particles formed in situ. In some cases, some of the gel went through secondary pyrolysis, but yeah, I think we got a good hang of how coatings form. Not only that, uh, understanding led to a basis for us to be able to now begin to tailor microstructures in solution precursor plasma spraying, um, from getting dense coatings to porous coatings to even attempt to begin engineering vertical cracks in these coatings, right? So that was useful. As a subset of that work, I think we also began looking at the origin of vertical cracks. So there's some very nice stuff that you could do by collecting particles in situ, looking at splats, and then uh, right, see how how energy considerations lead to crack formation. And yeah, so that was very useful. And then all that work that I showed you up to this point was done with radial injection. And then when when I moved here to Sweden, we had this lovely axial feed capable torch. And then suddenly that broadens the process window like nobody's business, right? So this was first shot, no struggle, and you get extremely nice coatings with what my colleague engineer calls dishwasher fluid. Use a dishwasher fluid as a precursor salt solution and get coatings which are thin, which are dense, which are controllable, and have a very wide processing window without falling away either in terms of crystallinity or the control that you desire. So let's move on from then solution precursors to use of suspensions, right? Why did I say that the use of suspensions is relatively easier? And that's because these additional steps, which are kind of involved only in case of solution precursors, are eliminated when you use a suspension. You almost start there, right? And then that also reflects in your energy requirements and ease of processing. I mean, just the number of variables that can mess things up are reduced, right? So as in case of SPPS, the use of suspensions also was originally driven by thermal barrier coatings. The reason being that very early on, the experimental work revealed that you have a possibility using suspensions to get some sort of a columnar structure, which is not exactly identical to electron beam derived columnar structures, but you know, you get columnar structures which are strain tolerant and therefore bear promise to be used as TBCs, right? So people even now typically compare EBPVD and APS, and suspension kind of lies somewhere in between and has advantages that are handpicked from both of these processes, which are relatively well established. It's much cheaper than EBPVD. It yet provides a columnar structure. It has potential to develop coatings with low thermal conductivity, and yeah, let me just say that you have a wide choice of suspension media now available, although most early work showed that if you are to target a columnar coating, you would have to use ethanol as a medium, which the industry does not necessarily like. There were also, as I mentioned, some reservations about deposition rate, but I'll show you that that was passed. So some quick results from our own work in our thermal spray group here by my colleagues. One was we have been using SPS for thermal barrier coatings for a long time. And we have demonstrated that one can almost control the columnar structure at will, right? You can control it for an identical suspension by varying the plasma spray parameters, or you could actually use different kinds of suspensions, right? By varying the type of solvent, by varying the loading rate, of course, and also playing around with the particle size that constitutes the suspension, right? And we also spend a lot of time trying to understand column formation. When do you get columns? When do you not get columns? There were, of course, theories which had been proposed, very logical ones, of course, but we spent a fair bit of time to validate experimentally the fact that we can indeed engineer columns or avoid them completely. For example, these are illustrations of how the coating buildup occurs when you use ethanol or ethanol water mixture, or what I'm not showing here is if you used water, you get entirely different coating formation. So as I was mentioning, if your target is getting a columnar structure, for most part, one would use ethanol, right? While use of water would give you a relatively dense coating, right? One advantage of trying to dig into this column formation mechanisms was also the fact that it allowed the thermal spray community to also get a hang of how to avoid columns, right? Which is necessary for many non-TBC applications. Yeah, so that's something to remember for later. I was talking about tailoring of microstructures. There are many ways you could tailor. I will show you some more examples, but these micrographs that you see here were from use of ethanol and water. You could also tailor microstructure by the manner in which you prepare the substrate for coating, for example. So now if you look at SPS coating development as a whole, kind of TBC specific in some cases, there are 2 or 3 areas that I am excited about. One is the development of new suspension media, going away from ethanol, for example, but still being able to get columnar coatings. There are also issues of shelf life and reuse of suspensions that are lying in storage for a long time, and these are of high practical and commercial relevance. And then, of course, there is this big chunk of applications to be harnessed if you're able to use suspensions with other thermal spray variants such as HVOF and HVAF. A quick example from Treibacher about using an alternate non-flammable suspension medium, right? I mean, they've shown recently, for instance, that one could move away from ethanol, use a non-flammable, at the moment proprietary medium, and still get very good columnar structure. That's one. And the other thing that comes out from this particular slide, which is a reconfirmation of what I showed earlier, that by increasing the spray power, one can get more pronounced columnar coatings and a higher deposition rate per pass. So good area to be in to development of new suspension media, for example. We were talking a little bit about throughputs, right? Now this is a TBC example, of course. Now you're beginning to reach almost 50% solid load via Z coatings using the suspension route, and these put you in a regime which is almost same as what you would typically get using a powder. As I will try and show you later if I have time. The same is true for chrome oxide, for example. Now you can, again, Treibacher has been our partner in some of this work. They've shown that you can bump up the solid loading to as high as 80%. And that puts you in a very interesting regime already, right? Some real numbers from our own work. Before my time, honestly. This was done way before my time, but this data from our lab here in Sweden. So when we started doing these TBCs using suspension yttria stabilized zirconia, the typical solid loading was about 10%. All other numbers here, but to coat a 300 diameter test specimen, 100 height, 100 height, with 300 microns would take us about 4 hours. It would consume about 12 liters of suspension, right? Fast forward to today, and we use barely 1.5 liters of suspension. We can accomplish this task in about 15 minutes, right? And then it begins to become really interesting for thermal spray practitioners, right? Kind of running slow here, but we have also spent a lot of time trying to tailor SPS thermal barrier coatings for enhanced durability by looking at a variety of different things. We have been looking a lot at chemistry, moving away from yttria stabilized zirconia, for example. We have been looking at microstructure, column density, and things like that. We have been looking at architecture, single layer ceramic TBCs and multi-layer ceramic TBCs. And yeah, it's been a long but very educative ride. Some examples from our group again. I spoke about multi-layer TBCs, trying to combine yttria stabilized zirconia and gad zirconate. Also looking at some other chemistries of interest in an effort to reduce thermal conductivity and enhance coating lifetime. Yeah, and we've been kind of, to close the loop, looking at not just microstructures, but how the coatings perform in thermal cycling situations, in burner rigs. The other interesting area has been to look at bond coat topography and the influence on coating microstructure and lifetime. So this is some of the work that looks at different pre-coating surface treatment on the bond coat, pre-coating of zirconia, I mean. And as you see, you get remarkable differences in column density that influences coating life, right? So let me spend a little bit of time now discussing whether, and this has been a question for a long time, is there life beyond TBCs and now environmental barrier coatings for liquid feedstock? Because until a few years ago, a very predominant portion of the literature was targeting only TBCs, right? But if you look around now, there indeed is some increasingly exciting work in areas that are phenomenally diverse. I mean, there is some work, especially from Christian's group, on anti-icing and super hydrophobicity. Quite a bit of that. We heard about biocompatible coatings to some extent over the last couple of days, and this is some data from our own group using SPS hydroxyapatite. We have now tried to build on this further by incorporating graphene and silver in hydroxyapatite. That's still work in progress, but at the moment looks pretty exciting. This is similarly some work that I did before moving to Sweden, and this was to target some antibacterial bacterial applications using solution precursors. I mean, very complex precursor. If you have good friends in the chemistry lab and have a beer with them, it helps once in a while, right? But it gives you coatings of a nature that are very hard to achieve by the powder route, right? In this case, the intent was to achieve Ti3+ self-doped rutile. And the chemistry guy said, you use this and you have a good chance. And sure enough, we did get coatings which showed extremely promising antibacterial performance using those kind of complicated solution precursors. Lot of action also in the area of electrode coatings. We are at the moment also working on solid state thin film batteries. There's been a fair bit of work in this group on SOFCs as well, as indeed elsewhere. So this is some of our early work a couple of years ago on SOFC coatings in collaboration with University of Toronto. So fairly interesting. And I just wanted to show this snapshot real quick of the immense possibilities that exist using both SPS and SPPS for realizing a vast spectrum of coatings, which seem complicated, but you do get them in a single step by engineering the solution precursors, for example, in a good way. Over the past couple of years, we have also begun to look at what we believe is a very large segment of coating applications in the industry, which is where and whether we can begin to use the suspension spray route to realize some tribological coatings, right? We kind of know what the boundaries are. We know what feedstocks are, what kind of materials are exciting. We know now pretty good how to tailor the suspension in a certain way. As I will show you in a little bit, there is also great promise in using hybrid feedstock that combines both powder and liquid, right? And we've also been trying to extend the use of such liquid feedstock or hybrids in not just plasma spraying, but also to HVOF first, and then more recently to HVAF, right? When it comes to wear, one of our earliest efforts was on alumina, because in a sense that's a low-hanging fruit. If you want to spray nitrates or citrates of aluminum and try and get in situ formation of alumina. What was interesting, however, was the ability to get phase pure alpha alumina if you sprayed it right. And this is not exploited enough, but there is great promise there, because as several of you who have tried to spray alumina powder using whatever route, could be HVOF, could be detonation, could be plasma. Even if you start with phase pure alpha alumina, you don't get alpha alumina in the coating, right? You get all sorts of different phases, but not so using solution precursor, right? If you control it in a good way. So this again is old work, but there's something in there which is worthy of being exploited further by combining that, not with radial feeding as this study was carried out, but with axial feed plasma torches, which give you throughputs that are interesting. So this was our modest beginning with SPS alumina using powder sizes which are 2 to 3 microns and lower, and we got pretty good wear properties, and that kind of encouraged us to move on to chrome oxide, for example, because this is an interesting material with kind of significant industrial applications. Anilox rolls is a good example. The other reason why it's a good example, good application to target, is because we believe that using suspensions can give you a much better as-coated surfaces, which will reduce the burden on polishing and grinding. yeah, which is an absolute must for an application like an Anilox roll, right? More about that later, but yeah, when we started, right, this is where we began with chrome oxide, and you can imagine why that happens, right? I mean, this is almost a column head, right? There's a tendency, if you don't do it correct, to uh, form columns when you don't want them and not get columns when you want them, right? So this is where we started, but yeah, as I mentioned, gradually we had gotten a pretty good handle of how to avoid those columns, and we've chugged along rather nicely. We get very good chrome oxide coatings with this was all with 40% solid loading, and we've built on that further. Uh, First was to see if we could carry that to an HVOF, and this is part of Yarko's PhD work. Uh, During my short stint at Tampere. And yeah, if you manage to optimize the process right, and we tried several things here, looked at spray distance, looked at employing a air curtain to reduce fines, you can get really good coatings, even using suspension HVOF, right? Which gives darn good wear properties, right? Uh, now the challenge is to kind of push the envelope further, right? And try and spray with higher solid loading, and therefore improve throughput, reduce costs, and stuff like that. So there's some early work using higher loading, but yeah, this is still work in progress, and there is quite a bit of effort now being invested, especially in Tribacher, for example, to take this out. Right, so alumina chrome oxide can be graduate to carbides, right? So this is kind of a one-off work, I must admit, on using titanium carbide and chrome carbide in suspension form, right? Without any binder, mind you. And we were kind of surprised to get pretty good coatings of titanium carbide and chrome carbide. Good wear properties. We have tried to build this further, and that's how the idea of hybrid processing using suspensions originated for us. But for me, the story is a little bit older. This was when my colleague in my earlier job, Shiv Kumar, was doing his PhD, and we had just begun to do some work on solution precursor plasma spray. What fascinates me about hybrid processing is the ability to create many different function dependent architectures utilizing building blocks that are so different in size, right? So if you were to combine typical powder splats, for example, and suspension, you can get a very unique structure in the form of a composite coating, right? And this can provide flexibility that otherwise does not exist, right? When I talk about building blocks, humor me for a minute and look at a typical splat which is powder derived, right? If you look at yttria stabilized zirconia, 7,500 microns end to end, right? And look at these YSG splats which are derived from a solution precursor. 1-2 microns max, right? So you're almost 2 orders of magnitude smaller, right? And there can be very interesting ways to combine these two building blocks by introducing powder and a suspension simultaneously, or yeah, if you want a composite, or sequentially if you want a layered architecture or whatever. I mean, imagination really is the limit. Or you could tweak these relative feed rates on the fly and get functional grading, right? So you can do many fun stuff if you're able to get this right, right? But by the time we got here, we were kind of addicted to collecting powder samples in flight and see what's going on. So the first question was, we were asking ourselves pretty mundane questions at that time. Can we first of all spray powders and precursors together? Is there a processing window that allows us to address powders and precursors at the same time, right? So we collected these so-called composite particles midstream, and they were very interesting. What looked like initially muck sitting on a powder particle actually turned out to be very fine particles which were precursor derived, right? So you immediately see what you want to see, right? You have a large particle which originates from the powder, and you have these fine particles which are formed in situ because of the precursor, right? So you can also see this impression on a splat, right? If you're careful and as biased as I am, imagine this is a big splat, right? From the powder, right? And all these tiny things are actually small splats, which are derived from a solution precursor. So even in a splat, you see this two entirely different scales that are there. And it reflects in many different ways, depending upon what's the application of interest. Here is an example where we had used yttria stabilized powder and the right kind of solution precursor to also form yttria stabilized zirconia, right? And that serves to toughen this in a way. So we found these coatings to be ideal when you wanted a combination of thermal cycling, lifetime extension, and good erosion resistance, for example. And we also done this for a couple of other systems at that time. Given the promise of this hybrid feedstock approach, we've here at University West spent a fair bit of time coming up with an elaborate arrangement that allows us to kind of effortlessly introduce both suspension and powder feedstock simultaneously or sequentially into our gun. And we've played around quite a bit with that now. We've formed composite coatings like alumina YZ. This is some work that Tanveer did using some of these coatings, and yeah, the benefit of using these kind of reinforced or deriving these kind of reinforced coatings using a hybrid approach was quite clear. I mean, much better fracture toughness, much better wear properties and stuff like that. Some more examples, alumina chromia. This is something that was done by Radek's group in Prague. And we've kind of carried this on in a sense. We are now looking at other exciting hybrid systems. One is incorporating carbides in, let's say, a matrix of triballoy. No good reason to use triballoy actually, except for the fact that we wanted to try this out and we had a triballoy 400 bottle sitting on the shelf there. But what this does is clearly shows you this multi-component splatting in situ, and then the ability, of course, to control the carbide content at will and get good properties, right? We've done since then many different things. Use this liquid feedstock approach to incorporate graphene in many different matrices, and it's not as if you need to go hunting for graphene. I mean, sometimes there's a tendency for us researchers to do that, but this is everywhere. And we've confirmed this with Raman. We've tried to quantify that. We've done wear tests with it. We've also, after this work with alumina, we've also incorporated graphene in yttria stabilized zirconia and thermal cycle that shown it to survive up to temperatures as high as about 400 degrees right? So yeah, we love this hybrid approach in a sense. Some of our recent work on, I was saying, solid state battery materials, thin film batteries. So we've essentially started with two different materials at the moment, lithium titanate and NMC. I think this is pretty good for a first shot, but this is subject of a recent project that we've got, and we're kind of excited about this. We are not self-sufficient in terms of being able to address issues of electrochemical activity, etc. But we do work closely with the battery lab at Uppsala University to do this kind of stuff. Right. So where do we go from here? We really wanted to do something wild and see if we could use suspensions with HVAF. I almost feel stupid now because at the beginning of my talk, I said liquid feedstock requires a lot of thermal energy, right? And now we have traveled quite a distance and are talking about deploying suspensions with HVAF, right? Yeah, we've done some fair bit of experiments with this idea and shown that if you're careful, if you have good engineer colleagues, you can do this. You can overcome the very high back pressure that, as one might imagine, is present in an HVAF, but still get the suspension through and do some pretty good stuff, right? One of these involved incorporating the same chrome carbide that I showed you earlier in Cornell to try and combine good wear properties with good corrosion properties with good wear as well, right? So we did that. More recently, we've attempted to incorporate graphene as a lubricating additive, let's say, to reduce friction coefficient in nichrome chrome carbide coatings. Yeah, we know this still needs some engineering work, but clearly there is early promise to be able to do this, right? We've also been using this hybrid approach to now look at a variety of solid lubricants. The hexagonal boron nitride is just one example, but you can do that. Also some good work combining capping of chrome carbide nichrome with graphene nanoplatelets and supplementing the graphene in suspension form by using the hybrid feeding. Yeah. I see that I'm almost out of time, so I would like to leave this here. I hope I gave you a flavor for what use of liquid feedstock can do. I think it brings a lot of new excitement to thermal spray. Granted that it is work in progress, but I think there are many new applications domains that beacon if we can do it right. With that, I would like to wrap up and with an invitation for you guys to visit us in Trollhättan if you're in the vicinity anytime. It'll be fun to chat up and show you around our lab. Thank you very much. I hope I didn't go over, Saurabh.
No, that's fine. Thank you so much, Professor Shrikant. That was really fascinating. And in the background, me and Alan were just discussing how comprehensive from the scientific perspective the talk was really. And we would be delighted to visit you for sure. We will travel you from the UK.
Super.
I mean, I didn't see any particular question raised. So I kind of understand that it already explains the talk was really very, very self-explanatory. But I have just two questions out of my own curiosity. So the first question is that the graphene incorporation in the deposition of alumina. Coming from a machining background, we are always very worried about the amenability of carbon to dissociate and react with aluminum. Is there any such concern when you go to use graphene containing carbon with alumina to form any sort of intermetallic, or is it not of a concern at all?
We've not seen it happen. Maybe we just got lucky, but we've not seen it happen when we incorporated graphene in alumina. We have, as I showed you, we have done this with both alumina and zirconia. We have done it with nichrome chrome carbide. More recently, we have done it with copper as well. What we are struggling with at this point is, in some cases, it does not show up as in terms of improvement in, let's say, coefficient of friction, as you would imagine, right? I mean, we had that expectation. We see graphene in there. It's confirmed by Raman. And as I said, you don't need to go hunting for graphene. There's a fair bit of graphene, but we don't see the tribo benefit that we are looking for in some systems. So I don't know. I wonder if there are wettability issues and such like, but there's clearly something that we don't understand too well at this point.
Okay. So the microstructural study needs to be further done, maybe in situ sort of wettability analysis.
Yeah.
Some other.
And we are not set up to do that, but that's something that needs looking at for sure.
I see. Okay. One last question, Shrikant. Because I see from your CV, you come from laser expertise. And I was just wondering, would incorporation of laser bring some additional benefits to the thermal spray plasma that you've been working on?
When you say laser, do you talk about tandem use of laser or laser as a post process? Because I think there are two different issues. I do remember.
Yeah. Well, actually, you can use laser in three ways. Of course, we have been discussing in the background also. But for example, if we have previously used laser for manipulating the Gaussian profile of plasma per se.
Right.
Do you envision any benefit there, or any other part of spray where you see immense benefit of incorporating it?
I mean, nothing comes to mind, especially when we use an axial feed plasma with the kind of power it itself has. I don't see the benefit of a laser there, but
je vais ouvrir dans une minute. Hein.
But yeah, if you have some thoughts, it'll be fun to try out.
Okay. Yeah. No, I have some thoughts for sure. Yeah. Okay. Great. Okay. Great. I mean, that was splendid talk, really, Professor Joshi. Thank you so very much. And if there will be any further follow-on questions, I'll route them to you, please. Of course. And, sure. And Alan and I are really grateful for this massive, splendid effort that you have put together in putting this.
Thank you.
Great. Excellent. Hello, Professor Armel. Can you hear us okay?
Yes, I hear you very clearly. Okay,
great. So I'd like to now welcome our second speaker for the day, Professor Armel Bordel, who is Editor-in-Chief for the Journal of Thermal Spray Technology. She is a distinguished Professor Emeritus at the University of Limoges in France, and she's engaged actively in research in the Institute of Research for Ceramics, shortly called as IRCER, and in Prothys, if I'm correctly saying it, a joint laboratory between IRCER, Safran, and Oerlikon Matco. Her research activities deal with plasma spray processes, physics-based model of plasma torch operation and process, creating their digital twins, coatings elaborated by emerging and conventional plasma spraying for transport, energy production applications, life cycle assessment of coatings and manufacturing processes. Armel is the author of 110 peer-reviewed scientific papers, 145 publications in various conference proceedings, and 10 book chapters. She is a recipient of several professional awards, including Hall of Fame of the Thermal Spray Society, Fellow of the International Plasma Chemistry Society, Fellow of ASM International, and Award of the National Association of Air Force Officers. She has to date supervised more than 30 PhD theses and 40 master theses in this area of plasma-based spraying processes. And two additional things I can perhaps add into that description is that it is, first of all, greatly a welcome to see a woman doing so much in the field of engineering, which is a very rare feat to achieve. Personally, I very much liked reading your papers. Like, you are very bold authors, particularly by selection of titles of your paper, which is very captivating always. So on that note, I would like to welcome you and very much look forward to hear your talk.
Thank you very much, Gaurav, for the introduction, and thanks to you and to Professor Alan Matthews for inviting me for this thermal spray week. I think it's a very good idea. I wish we had the same idea in my lab. Okay, I really enjoyed the discussion and the presentation of my colleagues the 2 previous days, and especially the presentation of Shrikant today. You know, my topic is very specific because I will not speak about coatings, but I will speak about the way we can produce the coatings. So I have chosen not to present any state-of-the-art about torch modeling. I think not a lot of people will be interested by this topic, but what I would like to do today is to share the interrogation we have about our models, especially if you want to set up a digital twin of the plasma spray process. Okay, so I would like to begin now my presentation. Okay. And first, I have to tell you that if you want to develop a plasma torch spray model, it's really a teamwork. You cannot do this alone. So at the lab, Rodion Zukowski, Christophe Chala, Vincent Ra, and in Oerlikon Medco, Ron Mols are working in the development of this model. Okay, and the work I will present today has been obtained by Rodion Zukowski in a joint work with Oerlikon Medco. As you explained, I'm working in the Institute of Research for Ceramics in France. This institute is part of the University of Limoges, but it's also part of the French National Center for Scientific Research, CNRS. In our lab, we have 4 teams, okay? And for the people working with coating, we are involved in the second team, which is called coating processes. And in these teams, we are dealing not only with thermal spray and cold spray coatings, but also with PVD and laser coatings. In this team, there are 47 persons, and our specificities is we are working in, we have developed a joint lab with the French Alternative Energy and Atomic Energy Commission, and for CEA, the French CEA, which is in charge of all the nuclear plants in France, and they are becoming more and more important for producing our electricity. We are developing some specific coatings that are able to sustain extreme conditions. But we have just, when I say just 3 years ago, we have set up a new joint lab with Safran and Oerlikon for thermal spray and PVD coating. The name of this lab is Proteis, and this lab comes with its own technological platform, which is called Sapphire. You can see the building here, this technological platform, and you can see here our lab. So it's about 400 meters far from our lab in the center of France, Limoges. And the good thing is, with this technological platform, we have access to the most recent equipment in PVD, but also in thermal spray. For example, we have now, and we will get very soon, the Surface One equipment from Oerlikon. And we have also access to all the equipment for testing coatings in real use, but for only aeronautical applications. Okay. Now, back to plasma spray. Why I have selected plasma spray, and we are using plasma spray. Plasma spray, it's very specific. If we compare the feature of plasma spray to the other plasma spray coating techniques, it's very special. First, it uses electricity as energy source, and this makes it possible to generate heat without taking care of the oxygen potential. And so we have the full control of the processing environment. Also, as you know, plasma is characterized by a very high energy density, very high temperature. We can go up to 20,000 Kelvin and even more now with the new plasma torches. We can reach very high velocity for the gas, up to 2,500 meters per second at the exit of the torch. And so this gas is able to bring very high heat flux to materials. With plasma, we can spray a large range of materials, but it's very well adapted to ceramic, and it's one of the reasons why we are using this in my institute dedicated to ceramics. Now, if we look at the thermal spray market, plasma spray is about 1/3. This was reminded by Professor Singh yesterday, and it's so an important process. Now, if we look at the process itself, it's not so different of the other thermal spray processes. For that, we can divide this process in 5 subsystems. Why 5? Because each subsystem will be described by a specific theory and specific equation. Okay, so first we have the formation of the plasma. Second, the injection of the material in the plasma jet, and these materials can be a powder, but as it has been reminded and well explained by Shrikant, it can be also a solution or a suspension. This material is injected in the plasma jet, processed in the plasma jet. After, it will be accelerated, melted, and it will impact on the substrate where it forms the coating. And we have also to take into account the motion between the torch and the substrate that will affect the growth of the coating, but also the coating and substrate temperature during the deposition process. But if we look at these 5 subsystems, they are interconnected, of course, but everything begins in the plasma torch. And so the plasma formation will affect all the other subsystems. And if there is some problem with this plasma formation, you will find the problem also in the other subsystem. If you look at the plasma torch, it's very simple. And the principle of the plasma torch is simple. It's not a so complex engineering tool, but its operation and the phenomena that are involved in this operation are complex. In fact, in the plasma torch, we have 2 main elements, which are the cathode and the anode. The cold gas is injected around the cathode. Now, in most of the plasma torches, we will have some swirling injection around the cathode, and some arc, will strike from the tip of the cathode to some point in the anode. It has to connect to the anode, and it connects to the anode thanks to a small, thin, but very hot and so very low density gas column. And because of this low density and hot temperature, this thin column will be subjective to some force from the cold gas flowing in the boundary layer close to the anode, but it will also subjected to the Lorentz force that are produced by the electromagnetic field resulting from the circulation of the current and the specific curvature of this thin column. And it will be also subjective to some heat phenomena because it will underwent a very intense cooling close to the anode wall, and at the same time it will exchange heat with this anode. So if you take into account this force balance, this energy balance, and also some possible phenomena, acoustic phenomena in the cold gas upstream of the cathode, you will get this type of arc voltage. The voltage is one of the most important feature of the plasma torch, and it's really the language of the torch. If you look at the voltage, if you look how it changes, how it varies with time, you can understand a lot from the operation of the plasma torch, how the arc is moving, if the electrodes are worn, and so on. So it's very important to look at it and try to understand what the arc is doing, depending on this arc voltage variation. It really reflects the stability of the anode arc attachment, and it's also proportional to the arc length. Okay. For any coating manufacturing process, the goal is always the same. That is how we can control the coating process and so control the coating properties. For plasma spray, it's not so easy. It has been reminded on the talk of Christian Moreau Monday. Plasma spray involves a large number of variables, and they are not fully controlled yet. If you think about the wears of electrode, but also the wear of the powder injector, suspension injector, and some clogging possibility, it's not easy to control everything. So now what the company are doing, they are using sensor during the deposition process. But as you know, we are all now entered in the digital age, and we can benefit of the new connection and the new network technologies, information and data acquisition system, and these are changing the way the people are thinking about coating manufacturing control. The idea is to go from a knowledge-based coating manufacturing to a data-driven and knowledge-enabled coating manufacturing. One of the most promising tools for that is the digital twin. What is a digital twin? I think everybody knows, but just to remind you, a digital twin is supposed to represent the coating process and coating performance in a digital world. Okay, it should be a high fidelity representation of the physical world. Okay, and it mostly contains 3 parts: the physical space, which involve the process, but also can involve the coating, the virtual space, that in that case, that involve both the process and the coating, and you have exchange of data and information between both. Digital twins are thought to be able to make the process more reliable and predictable. They can be used for process optimization, coating optimization. They can also facilitate the process control and so on. If we look at the digital twin for plasma spray, but it's the same for any digital twin, we can see 5 components. The first one is, of course, the physical space, and the second is the virtual space. And in between, you will have big data, machine learning, and connection between all these parts. And when you develop a digital twin, these 5 parts have to be considered at the same level. They are the same importance. Okay. Now, if you look at the virtual space, one of the components is a mechanistic model of your physical space. What is that? A mechanistic model is only a model that will use some theory based on physics law, chemistry law, mechanics law, and so on, to model and to be able to reproduce what occurs in the real world. So in this talk, what I would like to do today is just to share with you some interrogation we have about the model we are developing. We would like to implement this model or to use it in a digital twin of the plasma spray process, but as you will see, there are plenty of questions about the model. And there are 2 questions. I call them the preliminary questions. First, Which output do you expect from your plasma torch model? Before beginning any model, you have to be sure of what you want to get from your model, because depending on the output you are expecting, you can adapt and change your model. And also the second question is at which level we need to develop this model to have some accurate and reliable representation of the real world. Just to remind you, when you have a numerical model, first you will put down some assumption, and depending on your set of your assumption, you will select some equation. After, you will impose some boundary conditions that will limit the model, the physical space of your model, in fact. You will use some grid that will cover the physical space of your model. You will use some numerical algorithm, and you will also use the properties of the gas and their materials. And for that, you will get some prediction. So today, I just would like to show you, if you change one assumption or if you change one boundary conditions, how you can affect the model. I think it's important to see that, especially when you don't work, when you don't develop the models by yourself, because after, I think you will be able to ask more questions to the people that develop the model. Okay. Okay, so I will present first which are the input and output of the mechanistic model of plasma spray. Just remind which are the main output and main feature of the plasma torch model. I will show the plasma torch we are using. It's a commercial plasma torch that is developed by Oerlikon Medco, and we are working on the model of this plasma torch in the context of our lab with Safran and Oerlikon, the Proteus lab. And I will just show you, if you change one boundary conditions and one assumption, how you will affect the model. Okay, so from the mechanistic model of the plasma spray, which should be the input data, if you have in your mind to use it in a digital twin of the plasma spray process. It's important to understand that the only input data you can use are the ones that are accessible to the sprayer. That is what you have. You have a torch design, a part geometry, and you will select some process parameter. And you will also select the material you will spray, the materials of your part, of your substrate, and the gas. Because of that, you will have the properties and the gas and the materials, okay? And this should be the only input data of your model. That is, you have to limit as much as possible all the variables that you can adjust, okay? And from that, you will develop some model of plasma formation, of coating material injection, processing of this material in the plasma gel, coating formation. From the coating formation, you can get the coating architecture and microstructure. Shrikant has shown a wonderful picture of such coating, you know, and with the model, you should be able to produce such microstructure. And after using some specific codes, models, you should be able to predict the in-service performance of your coating. Okay. Now, the approach we are using in the lab, we are following in the lab is this one. We have decided to use as much as possible open source code, okay, which can be customized so that we can implement the physics we need to describe some specific phenomena involved in the operation of the plasma torch or in the processing of the materials. And we have also decided to use the code which is the best adapted to the phenomena we want to model. That is, for example, for plasma formation, we are using a specific code which is different from the one we are using for modeling and predicting the material processes. Okay, all these codes will exchange data through a transfer platform, and this platform is also fed with data coming from the real world. This data will be used to validate the prediction of the model, but also to begin the building of the digital twin. Okay. Our lab is partner of a French program, which is called Diadem, and this French program has the objective to build the tools, platform, service that can be used to develop digital twin. It's not only that, but part of this program is to develop digital twin for materials manufacturing processes. And in this program, we have a center which have expertise in material science and manufacturing, but also center which have experience in numerical modeling, data mining, machine learning, and artificial intelligence. So we rely on this program to develop the tool we will use for our digital twin. Now for the plasma torch model, what you want to get? First, of course, the plasma flow feed inside the torch, that is plasma velocity, plasma temperature. And you need also to have this temperature and velocity at the nozzle exit, something which is also very important. And it's the second main important prediction of the plasma torch model is where the arc will attach and how it will attach. This will make it possible to predict the time variation of the arc voltage and so that the enthalpy input to the gas, but also to predict the time variation of the plasma jet and the electrode temperature distribution. And this is the gate open to the prediction of electrode erosion. If you think at these data, they are not easy to measure inside the plasma torch, and even some are impossible to get. So we have to validate our prediction. And for that, what we can use? We have the arc voltage, the thermal efficiency of the torch, the thermal balance, but also the cooling water temperature and the post-mortem observation of the electrodes. All the model dealing with plasma torches for spraying, cutting, welding use the same approach, that is a magneto-hydrodynamic approach. So we solve at the same time the Navier-Stokes equation, the heat equation, and the Maxwell equation. And these equations have to be solved simultaneously. Okay, here we will use a cascading anode plasma torch developed by Earlycon Medco, which is the Simplex Pro plasma torch. This torch has a specific design. That is, if you look inside, you will see that the cathode and the anode are separated by some neutral insert. The idea is to force the arc to attach to the last string, and if possible, to maintain the arc attachment on the last string, so that we have high arc voltage and we have low arc voltage fluctuation. Also, it involves a very large cathode. Okay. Now, which are the main features of a plasma torch model to get reliable and accurate prediction? Okay. I am giving a list that this list results from our own work, but also from the literature and from the many publications by the labs working in this field, not only thermal spray, but also welding and cutting with plasma torches. So one of the important features is to have 3D and time-dependent model. We have to use the actual geometry of the torch and not a simplified geometry. We have to have the electrode in the calculation domain, and we need an accurate description of the cold gas injection in arc chamber. If the gas is injected with a swirling injection, you need to have the swirling injection as input data in your model. So just now, I would like to discuss about the magnetic field. So we will change one boundary condition for the magnetic field and see how it affects the result, and also discuss about one assumption and see how it affects the result. And this assumption deals with the consideration or not of the thermal non-equilibrium that exists in the electric arc. Okay. First, just why we need the electrode in the computational domain. If you don't use the electrode, if you have not the electrode in the domain, you have no choice. You have to impose some profiles of temperature and current density at the tip of the cathode. Okay, and this profile generally have this form, which is shown on the scene that you can see on the screen. And all this profile involves some parameters that you can choose. And if you want to develop a predictive model which is really, we can predict really the real world, that can be a twin of the real world. This is a problem because each time you change your process, you change any process parameter, for example, the arc current or the gas, you have to select these parameters. And it's not so obvious how you have to select them. You need some experiment or from experience and so on. Okay, also, if you don't have the cathode, you omit some part of the geometry of the torch, and experience have shown that this will lead some problem in the prediction. Okay. So the other solution is to have the electrode, and in that case, you only use arc current as the process parameters. Of course, now you have to solve the electromagnetic and energy conservation equation, both in the electrode and the gas. But in compensation, you will get the heat flux to the electrode and the electrode temperature. And so you have also more validation of your model because you can compare what you get with the observation of the post-mortem electrodes. Okay. So today I will just use one set of operating conditions. I will use pure argon, 60 liters per minute of argon, which is injecting with an angle of 25 degrees. The arc current is 500, and the anode, the nozzle diameter is 9 millimeters. In the model, we have implemented the actual materials, and that is the tungsten is doped with lantana, and we are using copper in the nitrode and anode part. And the computational domain extends from the rear of the cathode to the nozzle exit, and we have added an outside domain which is as long, nearly as long as the torch itself. And there is another assumption. Up to now, we have no choice. We have to select this assumption that is considered that we have brand new electrode. That is, the surface of the electrode is smooth. Okay. Why it's important to have an accurate calculation of the magnetic field and which boundary conditions we should use to calculate it. Why it's important? If you look at the momentum conservation equation, sorry for this equation, even if you don't know it, there is no problem. Just look at the source term which appears in this equation. This source term depends on the magnetic field and the electric current density. So if one of them is wrong, for sure, the velocity could be wrong of the gas. And also, we need an accurate prediction of the magnetic field to simulate the magnetic constriction of electric arc. In fact, if you have some instabilities in the calculation of the magnetic field, you will have some instabilities in the calculation of the Lorentz force, so also in the plasma velocity and in the plasma jet. Okay. Now, when you look at the real world, you have the magnetic field, which is the magnetic field, and the source of the magnetic field is the circulation of the current, so the electric current density. Okay, and they are linked by the equation you can see here. Okay, but in the numerical work, it's different. The magnetic field will be derived from the magnetic vector potential A by this equation. Okay, so when you think about the boundary equation, boundary conditions, you have not to think for B, but for A. And generally, there are two types of boundary condition we can use. One is to impose some null flux at all the boundary except far from the arc where you put the value equal to 0. The other boundary conditions, which is perhaps more demanding, is to calculate the value of A at all the boundary by using the Bureau-Savart law. You have surely seen this law in your previous studies. Now, just look at the difference of result we can get when we change these boundary conditions. Here, we have used the null flux on all the boundary conditions. And when you think at that, you look at the field you get, it seems that it's not so good. It's very strange. You can see that especially at the cathode tip, at the nozzle outlet and the anode wall, they look wrong. While if you look at the prediction we get now, when you use the Bureau-Savart formulation for the boundary conditions, you get what you are expecting. That is the maximum value of the magnetic field are at the cathode tip, at the anode attachment. And also you see that this profile is very similar to the one you can get if you consider a cylinder with a uniform current density, and it's what was expected. So first, for the people that want to deal with model of plasma torch, don't forget to draw some picture of your magnetic field before going further with your model. From that, you will learn a lot about the accuracy and reliability of your prediction. Okay. Now, second point is about the assumption of the model. Generally, the models of plasma torches can be ranked in two categories. One deals with local thermal equilibrium. The second will deal with what we call a Tutti temperature. Local thermodynamic equilibrium consider only one temperature for all the species in plasma. That is, we assume that everywhere in the plasma there are enough collision between the electrons and the heavy species so that they have both the same temperature. It's a this model is easy to handle. Okay. And the properties of the plasma that you need to solve your equation are easy to find. Generally, you can find them in the literature, but they really fail to give real prediction in arc periphery. The second category, which is generally called the Tutti models, use two temperatures, one for the electron and the other for the heavy species. Of course, now you have to solve two energy conservation equations, and the convergence of the model will be difficult to achieve. Okay, but in compensation, you have more accurate prediction in arc periphery. Okay. But one of the major problems with this model, if you want to use this model for plasma forming gas mixture with hydrogen and argon, for example, nitrogen and nitrogen or helium and argon, you will not find the properties of the gas in the literature, and you have to compute them. Why there are thermal non-equilibrium in the arc? First, there are some in the arc fringe. You know, when the arc comes close to the electrode, for example, close to the anode, which is very intensively water-cooled, the arc will be also been intensively cooled down. And because of that, you know, you will not have enough collision between the hot electron and the heavy species when it goes below 8,000 degrees. And in that case, now the electric conductivity of the gas will be too low to allow the current continuity. So if you use a LTE model, you have no choice. You need some numerical tricks to have the continuity of the current between the arc column and the anode. Generally, there are some other tricks, but the most used is to impose, okay, it should be on the other side, is to impose some high electrical conductivity close to the anode wall to be able to the arc to go through this cold boundary layer. Another place where you have a very high departure from equilibrium is the interface between the cathode and plasma, or anode and plasma. If you look at this very specific location, you have a layer of a specific, you have, sorry, a stack of some specific layer in which the properties of the metal has to be progressively adapted to that of the gas, and the electron have to be progressively adapted to the issuing from the cathode have to be adapted to the plasma. Okay. If you want to take into account this non-equilibrium, thermal non-equilibrium phenomena, you have now to solve two energy conservation equations, one for the electron, the second for the heavy particle temperature. And you should also add some model about this layer that develop close to the electron. If we look at the result we get, with the LT and Tutti for the current density distribution, you can see both on this picture. You can see that there are some striking differences at the location where the arc attached. If you look at the cathode attachment, it's much more constricted and narrower with the LT model. Okay. Now, if we look at the anode arc attachment, this is a striking difference. With the LT model, it's constricted, while with the Tutti model, it's diffused. If we look now at the velocity and temperature profiles we get at the nozzle exit, this is a cross-section of the nozzle, and you can see here that with the LT model, we have some rotation of the arc, okay, and this rotation is induced by the swirling injection of the gas. Now, if I look at the nozzle exit, but with the Tutti model, you can barely see any movement of the arc. Okay, you have just to see that here. Okay, but the arc hardly moves. Okay, but which model is correct? For that, what we can do is to look at the anode. And here it's an anode that have been operated for 5 minutes. After, it's difficult to compare with the prediction because you have some where the cathode, the anode, sorry, is worn, and you don't know if your prediction are still correct. Okay, so you can see that the erosion is uniformly distributed all around the bottom edge of the anode. So this seems to confirm that the Tutti model gives more reliable prediction. Also, what we can do is to compare the arc voltage we are predicting by both models to the experimental one. With the LT model, the predicted voltage is about 92 volts. With the Tutti, it's about 25, and with the experiment, it's about it's 75, sorry, and with the experiment, it's about 71 volts. Okay, so you can see that we are becoming closer to the experimental data. Now, what we can do is to implement this cathode sheath in the model. And the difference appears mostly at the cathode tip, of course, where the model is implemented. And what we can see that it is much more, we have a higher current density at the cathode tip center when we have the sheath model. In addition, when we have this sheath model, we don't need to use some variable selected by the user, like the cathode voltage drop at the cathode, okay? Because this will be predicted by the model. So with the sheath, we have some important difference in the prediction of the current density at the cathode tip, okay? If we look at the field we get, for example, the plasma temperature field, we have also some difference in the two fields. As we have a higher construction with the schist model, we will get some higher self-induced magnetic field and Joule power, and so higher plasma temperature near the cathode tip. Is it important for the prediction? Yes, as you will see here, you can see the distribution of temperature of the cathode tip without schist model and with the schist model. And if we compare it with some cathode, that new cathode that has been operated for 5 minutes or for 60 minutes, you can see also some melting of the tip of the cathode, and the higher temperature is well predicted by the schist model. It's assumed that this melting is produced by the evaporation of the dopant, but we don't now, we have not taken into consideration the diffusion of the dopant in the cathode and its evaporation. This is for the future. Okay. Now, a possibility is also to look at the voltage. And now you can see that with the cathode schist, the predicted voltage is 71 volts. That is, we are very close to the experimental one. Okay. Now, if you look at the profile you get at the nozzle exit, okay, here for velocity and here for temperature, what you can see is LT give really not so good prediction for the velocity. At least we assume that they are not so good, but for the velocity. But for the plasma temperatures, there are not so much differences in the prediction at the nozzle exit for the temperature if we have LT, Tutti, and Tutti with and without schist. So depending of what you get, because you can use the profile you have predicted from this model for a model of material processing in the plasma jet. Okay. In the nozzle exit, perhaps the effect is not so much important with the inclusion of the schist in the model. But now, if we look at the temperature of the electrode and of the neutrode, you can see that because we have because we have this higher current density on the cathode tip, we will have a higher heat flux to the electrode and the neutrode. As you can see here, and you can see here the variation of the heat flux due to radiation along the neutrode stacks. And you can see that it changes. This is the anode ring. Here is the neutrode stack. Here is the cathode tip. And you can see that you have a rather strong increase when you add these cathode sheets. So as a conclusion, an accurate and reliable model of plasma torch operation can be used now as a basis for the development of a digital twin of the torch first, because it's important also to have a digital twin, not only of the whole spray process, but also of the torch itself. This is very important, in particular for the manufacture of the torch, like Oerlikon Metco or Metec. Okay. And it can be used also as a basis for the mechanistic model of the plasma spray models. But for that, it should include the electrode in the computational domain. It will consider the thermal non-equilibrium in the arc fringe, but also at the interface between the electrode and the plasma. Sorry. And it needs also a very accurate description of the magnetic field. Okay. I will stop my presentation here, but in fact, there are many other questions about this type of model. And for example, we don't take into account the chemical non-equilibrium. And one of the key issues is how we can predict the anode where this is an important point and a weak point in thermal spray. It's how the anode and especially anode will run during the process and how this will affect the processing of the materials. Okay. Thank you very much for your attention.
Thank you very much, Professor Bordel. That was really a good effort from the modeling perspective. If there is any question, I would like to invite anybody to ask. Otherwise,
okay, I know that it's not a so simple topic if you work with coating, but I think you have to know about that. And you have to know also in a general way about the models. You know, now we have computer codes that we can buy, for example, or you have access to some open source codes, but you have really to take care of how you use this code. Huh? With this code, you always get prediction, okay, because they are well done, well developed by many people. But we have really to ask questions about the way this model are used, you know, which boundary conditions are used, which are the assumptions of the model. These are very important points. And also, and sometimes we don't know about that, which gas property are used. When you think about plasma, you have really to know which are the gas properties which are used and which properties of the materials are used. I'm sure that now, you know, most of the labs involved in thermal spray, you have seen that with the previous presentation. Most of the company involved in thermal spray also have strategies to develop digital twin. So you have to develop this mechanistic model of the thermal spray process, okay, and even of the coating. But I think it's not so straightforward. You have really to take time to think about the model, what you are doing with this model. You know, perhaps it's because I'm too old, because I am this question. When you are young and brand new in this field, you go like that, and perhaps you get much better result what you can get because you have no question. But I think sometimes it's good to stop and think, okay, what you get, what you input in your model and what you get really. It was the objective of my talk, just that people have some question about that.
Absolutely. I mean, one question has come in the audience, which is it possible to predict live arc shifting as a function of gun usage time?
To predict, sorry, the
live arc shifting as a function of gun usage time. So over time, can we predict the shift of the arc location?
This is really an excellent question. Okay, it's not so easy because for that, if you have to predict the erosion of the anode and cathode. Okay, and up to now, if you look at all the models in the literature, everybody supposes that we have a brand new anode with a smooth surface. Of course, we have all the people working in the field of plasma torch model have that in your mind, how to make this possible, okay? How to be able to have a high fidelity model of the life of the plasma torch during operation. And in fact, this is a prerequisite if you want to develop a digital twin, but I think it's still a long way. So I think we will develop digital twin without this feature, okay? And we will adapt from data from the literature or with data got from during the deposition process, because it's not so simple. For example, only for the cathode, you have to think and to model how the dopant will diffuse in the cathode. You know, all the cathode now in DC plasma spray torch, most of them use tungsten for the cathode, and they use some dopant to decrease the work function so that it's easier to extract the electron from the cathode. But this dopant will diffuse and evaporate and after recondensate on the cathode tip. So it's one of the points you have to take into consideration if you want to predict the evolution of the arc during the life of the torch. So it's a very important point, but I think there is still a long way, at least in our lab. Perhaps some labs are more advanced, but for us, we know that it will take time to do this. We have that in mind, of course, as everybody working in this field, but it's not so easy.
Yeah, Gustavo, would you like to ask?
Afternoon, very interesting presentation. So my question relates to integrating the whole model from the processing itself of the plasma up to the mechanical property or whatever other property you might be interested on the output. Has it been done, or is it feasible to integrate the whole system, right, from processing to properties in a digital twin?
Okay. Up to now, to the best of my knowledge, this has not been fully done for thermal spray. If you look at different fields, for example, additive manufacturing, but not with cold spray, you can see some example, and in other field in manufacturing, this has been done. But remember that thermal spray, it's difficult because you have this process itself, which is complicated. But there are some parts that have been done in different labs. For example, there was very good presentation by Christian Moreau that tackles this topic on Monday. And if you look at what they are doing in Toronto, for example, or in other labs, Robert Vasson lab also, in many labs working in thermal spray, you have some part, but nowhere it has been completely done. But people are trying to do this now. Okay, this is really the goal of most of the lab working in this field. And I have put down some questions for the plasma model, but think that you have to put down a lot of questions also for each model you will use. Okay, because in each model you have some assumption. There are always some phenomena which are not easy to model. There are some phenomena that we don't know very well. For example, Shrikant has very well presented the coating formation in suspension and solution plasma spray. We don't know all the phenomena that will lead to this type of coating. Okay, so how do you want to model something if you don't know what occurs in the real world? Okay, so I think the people working at the lab level, and I really have a lot of admiration for the people that work in the real world, and the people working in the modeling world, in the virtual world, have to work hand in the hand, because we have to exchange data the whole time. Each time they improve their knowledge, we can improve our model. Okay. So I don't know if I answer your questions, but.
Yes, actually, you answered very clearly. You know, there are parts and nobody has really integrated together. So that's our grand challenge yet. So thank you very much.
Yeah, but I think, this could be a very interesting challenge for the thermal spray community. And it could be also a very interesting topic that should be carried out not only by one lab or specific lab, but it could be really a very interesting European project, for example, or international project. We really need international project now. It's very important to show that we all can work together, believe me.
Okay. Maybe a follow-on question on that, Professor Bordel. Would you attribute this gap in prediction from fundamentals to what we get at the end? Would you attribute this more towards the scale of multiphysics domains that are there required to be understood, or our inability to actually capture the entire material aspects?
Both. No, it's an excellent question also, but no, they are both very important. Both. No. And also, when you want to go from the real world to the digital world, we have this aspect of multi-scale modeling. Okay, the time are very different. The characteristic time of the phenomena involved in each part of the process are different. It's very fast in the plasma torch. Okay, and very different at the coating formation level and so on. And Shrikant was showing that a process can last 10 minutes, 15 minutes. I think he said 17 minutes now, 14 to 17 minutes. Okay, to model such a long process for us, it takes 1 day to model 1 millisecond for the plasma torch. Okay, operation. So it's still a long way to go. to have a real. So it's why we need some reduction of models, some statistical model, and some intelligent artificial to go from our model prediction to the real space, for sure.
Okay. That's it. I think, Professor Bordel, very well done to both the speakers for today, Professor Joshi and Professor Bordel, to help conclude on time this Thermal History Week's third day. And if there are no more questions, then I think we can close the day today with the last day tomorrow with the ECR-driven presentations from Professor Sanjay Sampath's group and my group, as well as Professor Harpreet's group. So on that note, Alan,
many thanks from me as well. I'm really delighted that we have such excellent speakers, and hopefully, and don't forget that these talks are all available via YouTube online via the network's webpage.
Thank you.
Thank you very much again.
Thank you very much.
Thanks very much.
Thank you so much. And we do look forward, Professor Bordel, to enter into some sort of European project for sure.
Yeah.
Thank you.
Although Brexit has happened, but it does not limit the science to carry out.
Thank you. Au revoir.
Yeah.
Thank you very much once again.
Thank you.
Bye-bye.
See you.
Bye bye. See you.
Bye, Armel. See you again.
Bye.
Bye. See you again. Yes, soon. I
Bye.
hope in
Yeah.
Vienna. Soon. Bye.